Alright guys, so let's continue our discussion of epoxides here. So in our last lecture we saw how these epoxides could form, and now we're going to talk about one way that they can open up, and that's under acid conditions. So we see H3O plus here, so H3O plus is this, right? So the first thing that will happen in this reaction is that we're going to swing over and grab a proton. That'll give us this intermediate with a positive charge on it. And just like before, we have a three-membered ring, so three-membered rings open up anti to each other. And also that carbon right there, this one that I'm highlighting green, this is the one that has the bigger delta plus on it, right? Because it has two R groups on it. So water's going to come over here and attack there, and we'll have that open up. Right, so there's the OH that was here, and there's our OH2 plus with its lone pair right over on the other side. And then the last step of this reaction is that you have water coming over, grabbing an H, right, and that makes your trans diol. So we have our OH groups opposite to each other. So in chapter 14, we're going to see how this can occur under basic conditions. But in this chapter, we're just going to talk about acidic conditions. So again, to point out here, we've made a trans diol. There's a couple reagents that we can use that will make cis diols. So cis diols can be made by using osmium tetroxide. That's OSO4, in the presence of peroxides. So it gives you a Syn addition, and for the osmium tetroxide, it's a couple things. It's expensive, it's toxic. You form this solid compound which is volatile. It can make you go blind, so there's problems working with it, but anyway, it's a reagent that's used. But you take an alkene and you add it, and you get a Syn diol. So let's look at the mechanism here down below. So mechanism involves OSO4. So OSO4 has that Lewis structure. And we're going to see electrons coming up to one of the oxygens. Right? Electrons coming over to osmium. And then a set of electrons coming down here, like so. So what we're going to form here is something called a cyclic osmate ester. So you can see here that the oxygens are kind of added right on the same side, so you get that Syn addition. And the removal of that is not something that we're going to talk about the second step with hydrogen peroxide here. But the end result is that you get an OH and another OH Syn to each other. Now a couple little notes about this, because this is the p orbital that's reacting. You have to consider the top and the bottom attack here. So we get a mixture of possible stereoisomers depending on the molecule itself and stuff. So OSO4 is the first one that we can use to do that, and then K1O4 with hydroxide is the second one. So notice here the K1O4 comes in two flavors. One is cold, dilute, and then the thing that we'll see on the next page is warm and concentrated. So what forms here is a Syn addition, and it works the same way almost as we saw the last reaction occurring. Right, you see your MnO4, except now you have a minus charge here, right, on the oxygen. And we see an electron flow where we come down to the oxygen and put some electrons on the central atom, and then we're going to come over here and grab a hold of a carbon on the other side. So that gives us this. So that side of the molecule wants to stay away from the double bond because it's bearing a negative charge, and the carbon-carbon double bond is the nucleophile. So this thing is called a cyclic manganate ester. And then sodium hydroxide kind of takes care of the rest of this and gives us the Syn diol. In addition, you get a brown PPT. Now, again, the mechanism for that removal with sodium hydroxide, it's not something that we're going to talk about this semester. So we just need to know the observed reaction in this first little step here of the mechanism. All right, so a couple other reactions left. One is called oxidative cleavage. And cleavage is when you break a carbon-carbon double bond. So we're going to see that there's two reagents that we can use to do this. So one is ozonolysis and the other is warm concentrated KMnO4. So in ozonolysis you use O3, it's ozone, and that bond is broken. Right? You form this intermediate, which this intermediate is not something you guys need to worry about. So they go through the mechanism of this in your textbook, but we're not going to learn that mechanism. I never really teach that mechanism. So we're just going to learn the end result of this, which is that you form a ketone and an aldehyde. So it's like this thing is opening up here, and then you're going to put oxygens on both ends right there. Right, so you just cleave a double bond and break it in half. Now, the one thing to point out is that the reaction stops here with the aldehyde. So because the aldehyde has an H on it, it has the potential to be further oxidized. The ketone doesn't, right? It's got two R groups. So we leave that kind of like it is. Now, if we want to continue that reaction, then we have to use something that's stronger and better at oxidizing. So we use KMnO4, and we use warm concentrated. So warm helps give energy to the reaction. Concentrated means we just have more of it, right? So reaction to this, again, we're not going to learn the mechanism, but let's look at an example here. So let's take something like this fellow here. And then the way that you're going to see this reaction is with two steps. So step number one, you're going to see typically warm, concentrated, right, KMnO4, and you might see some type of a solvent or a base there too, like sodium hydroxide. So at first glance, we're going to cleave those bonds. Okay, so on the one hand, if we look at the kind of the bottom half of the molecule, we're going to get this guy. That's going to be an oxygen. Right, so we insert oxygens here and here, and we kind of open it up. And on the other side, we get another oxygen. So this top thing right here is a CH2, right? Those are CH2s. So that's going to give us a C, H2, double bond oxygen, right? In fact, we get two of those because the CH2s are both at the end there, right? So we get both. Now, these things can continue to react because, look, we have an H atom here. So this ketone, this is a ketone. Ketone stops reacting, but this guy is an aldehyde, so we can continue to react. Same thing up here, you got these two H's. It's kind of like a double aldehyde in some regards, right? So we're going to continue that reaction here, and we oxidize further. So we're going to turn that group into an OH. So you can't put another double bond there, right? Because that's going to be 5 bonds to the carbon atom. So this guy stays the same. And then down here, you still got this. And then we get we get this. Now I want to point out that you're still in KMnO4 and hydroxide. So pretty much like the second that this is made, because you're in hydroxide, this gets deprotonated, and what you're left with is an O-, right? Because you can't have a carboxylic acid hanging around in a basic environment. And then this guy over here does the same thing. So, right, it's going to form O- carbon, O- here. And then the second step, so this is step 2, is adding H3O+. We call this an acid workup. So add H3O+ there. That's just going to protonate the end of the molecule, right? So we'll get our OH group back. Okay. Now as far as this other guy, he's kind of interesting. So what he becomes is that guy. So this is carbonic acid. It is H2CO3. And that is going to want to decompose. It decomposes into CO2 plus H2O. And because CO2 is a gas, that's what that arrow up means in chem, it pulls the equilibrium to form only CO2. So what that means is that these terminal guys down here, whenever we see terminal alkenes, that just means the alkene that's at the end of the molecule, those things are going to have the end result of becoming CO2s. So this guy and that guy become CO2 down that chain of events. And then our aldehyde here becomes a carboxylic acid. Okay, so those are the two different ways that we can do those oxidations. Now, a couple things pointing out, this warm concentrated is what we're going to be using to do this. That's what I tend to use. There's some other things that you can use. It can be acidified and stuff like that, but I tend to say just warm concentrated and typically basic, but you'll see acidic in there sometimes too.